So we're going to take a look at some chemical bonding now. We've already taken a look at our atoms and our element, our table of elements here. So I'm going to kind of scoot to the side, and just as a reminder, we talked about our atom. Remember, in the middle here, we have our nucleus. And then within our nucleus, we have our protons and our neutrons. And then kind of floating around our nucleus, we have our electrons. And remember, we talked about the type of element it is. We can see that on the periodic table here. Let's say carbon, that's a good example. Carbon, it has the 6 at the top there, which means that it has 6 protons. And then we also said that if it was stable, then that meant it also had 6 electrons floating around. When we talked about that, we talked about it as it relates to the different orbitals or the different shells. So remember, we have our nucleus in the middle, and then around that nucleus we have our first shell, or first orbital. And recall how many electrons we would find in our first shell. So the first shell, right, we had 2 electrons, so a maximum number of 2 electrons. Then we had a second shell after that. And in our second, how many electrons? Maximum of 8 electrons. And we also found that in the third shell as well, which is as far as we went. So if we are looking at carbon specifically, we said it has 6 protons, and if it's stable, it has 6 electrons. So we already have 1, 2 here in the first shell. Then we have 3, 4, 5, 6. In the case of carbon, then that meant that in our outer electron shell, we were missing these electrons, which meant that it does not have a full outer electron shell. That's also called the valence shell, or valence orbital. So what we talked about was the fact that carbon, in this example, we're using carbon, is then going to be looking to interact with other atoms. We also looked at sodium. And when we looked at sodium, sodium's a little bit larger here. It has 11 protons, which means if it's stable, it has 11, or if it has the same, if it has 11 protons, and it has 11 electrons. If we have our nucleus in the middle here, then we have our first shell with 1, 2 electrons. And then we want to go to the next one. 3, 4, 5, 6, 7, 8, 9, 10. That gives us our 8 in that one, so that's full. And then we needed to go to another one and put 1 up there to give us our 11 electrons. So this is kind of where we ended, was we took a look at sodium, and we noted that we had to go to that last shell there, that third shell, and it only had 1, so we were missing this, missing here, because remember we want 8, so we're missing 7 in order to make this a happy little stable non-reactive atom. And so what this means then is that sodium is not stable and it wants to interact. And what it wants to do is it either wants to fill up this outer electron shell by getting, let's say, adding 7 more electrons to make that stable, or in order to make a stable outer shell, what it could do is it could get rid of, and what we actually see happen is it'll get rid of this electron here. So we remove this one, which then leaves us with an outer shell being the second shell. And then it has a happy outer shell, and then it's done interacting, done reacting. When this happens, then what we see is we're going to change the charge. Okay, so remember that electrons are negative. Let's move over here. Our electrons are negative, so what we're going to be talking about is an adjustment in the charge. Let's scoot this over here. So let's take, for example, our sodium. Now what we're talking about are ions. And ions are atoms, or molecules, that carry a charge. And this is because of an imbalance in the number of protons and electrons. So ions are very important for physiology because these charged particles play a major role in the function of the brain. We're talking about the nervous system and sending information along the neurons and along the spinal cord, etc. In the heart, because we're sending messages, basically an electrical signal throughout the heart in order to make it pump. The muscles also sending an electrical signal. So we'll see things. We'll see a lot of ions. So we'll see a lot of sodium ions. We'll see chloride ions. We'll see potassium ions. So we're going to see a lot of ions as we talk through the semester and we look at each of the different systems. So it's important to understand that ions carry a charge. So if we look at this one, for example, we've talked about sodium a little bit. Notice that there's a plus sign here. So this is a positively charged ion. Chloride here, you can see with the negative sign, is a negatively charged ion. And so the way that we get these charges is just what we were looking at down here. So we said that in order for sodium to be happy with its outer shell, it would either need to gain 7 electrons or lose 1 electron. So if we look at the energetic exchange there, sodium can either be out in the world trying to interact with different atoms to gather or gain up 7 electrons, or it can simply lose 1. So energetically, if we take a look at that, it would be much easier for sodium to just lose an electron versus trying to gain and gather up 7 electrons from somewhere else. And that's what we see happen. We see sodium is going to lose its electron. So I'm going to just kind of redraw what we have down there with our nucleus there. We have our inner shell there. We have our second. We'll just fill this in. Remember, we're talking about 11 electrons here. And then we have our third shell. And remember, it only has 1. I'm going to put it over here now so we can take a look at this. All right, so now we're talking about having 11 electrons here because we have 11 protons. Now, we mentioned that losing 1 electron is going to be a lot easier than gaining 7 other ones. Now, if we keep in mind that electrons are negative, what we're doing then is we are decreasing the amount of negativity, right? If we're losing some negative, right, we're losing or decreasing the amount of negative, what we're actually doing is we are becoming more positive. Does that follow? So if we are going to ditch this negative, we're losing some of the negativity, then we're actually becoming slightly more positive. And so when we do, when sodium, when we see this, and we'll put sodium, when sodium does lose this electron, this negative electron goes away. I'm going to erase that now, so we're going to turn it into an ion. So we're going to lose this negative electron. Get a bigger eraser here. So we get rid of this, then that means we no longer have this outer orbital, right? But now what we have is this as our outer orbital. And now it only has 2 orbits or 2 shells, but it's happy because it has 8, which is the number it wants in its outer shell, and then 2 in its inner one, which of course makes sense because that fills up first. But then we put this plus sign here because now it's positive, because remember we have an imbalance now between the protons. We have our 11 protons in here, and then now we have 10 electrons. Since there's more positivity by 1 than there is negativity, right, 10 versus 11, we have a single positive charge here. So sodium is a positive ion. When we talk about ions, in this case, we're talking about sodium first. It's a positive ion. A positive ion is called a cation. So a positive ion is a cation. I remember this because I like cats and I think of them positively. So a cation is a positive ion. So now sodium, actually when it's out in the world, is a positive ion or a cation. So it's positive, it carries that charge, and what that means then, it is going to be attracted to negative ions or to negative regions. And we'll talk about that a little bit further in just a moment, but let's go with our chloride example. So if we take a look at chlorine or chloride, actually let me decrease that. If we look at that, let's take a look at it in the same way that we took a look at sodium. So we have our chlorine or chloride. This is our nucleus. Around the nucleus, we have our first orbital. If we're looking, let's see, at chloride, just a note here. Chloride has 17 protons, so we're going to be looking at 17 electrons. All right, so we already have our 2 here. Let's do our next orbital. So we're at 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 7 more. Let's go to the next one. 10, so 11, 12, 13, 14, 15, 16, 17. All right, so we're at 17 electrons, and we have something somewhat similar to sodium here. All right, so we have our chlorine here, and if you note, right, our first orbital is full, as it would be, because we have more than 2 electrons. Our second orbital has 8, which means it is also full. Our third shell, or third orbital, however, is not full, so we're missing an electron here, right? So we have 1, 2, 3, 4, 5, 6, 7 in that third one. We're missing number 8 there. So the same way that we looked at sodium, right, chlorine here could either lose, right, get rid of these outer 7 electrons. So get rid of those 7, so we decrease our shells, and we're down to this second shell only as the outer shell. Or it can then gain 1 electron. So if we gain an electron, it goes right there, and then we have a happy outer shell, and then it's going to be happy and done interacting. So as we mentioned with the sodium, which is easier to gain 1 electron or to go around losing and getting rid of, trying to pass off 7 electrons. Well, what's easier energetically here is to get an electron, and that's what we see chloride doing. So what he does here, he, of course, gains an electron, not of course. And then, in the same way that we looked at the protons versus electrons in our sodium, if we still have our 17 protons, which we do, and now we have gained an additional electron, now we no longer have 17 electrons, now we have 18 electrons. And in this case, we have gained more negativity, right? So we have more negativity, more electrons, which are negative, than we have positivity, or positive protons. So in this case now, we have chloride, which is a negative ion. All right, so we have 18 negatives and 17 positives. Those together are going to give us one single negative more than a positive. So we have our negative chloride ion. Our negative chloride ion then is called an anion. This is our negative ion. You can remember this as a negative ion. So a negative ion is an anion. So we have our anion here of chloride, and then, or chlorine, and then we have our sodium ion over here, which is a positive ion, which is our cation, and our negative ion, which is an anion. Now again, just like when we talked about with sodium, it's more positive. So positive is going to be attracted to negative. Over here with our chloride ion, our negative is going to be attracted to the positive. And so this is actually why we see sodium chloride. So sodium chloride, let me just actually zoom this down a little bit. So sodium chloride is what we think of as, or is, table salt. So our table salt is actually NaCl. Notice that there's no positive or negative, and this is because when our sodium, Na, and our Cl come together, then we see this losing and gaining of electrons. So again, our sodium is going to try to grab onto, or let me erase that. Our sodium is going to try to get rid of its electron that it has in its outer shell, which was making it want to interact. And then our chloride actually wants to gain that electron. So just like we saw up here, rather than me drawing the whole thing out again, so remember our sodium had this shell over here, And then we said it has its single electron out there. Was it easier to gain 7 or to get rid of 1? We said it's easier to get rid of that 1. It does. It gets rid of that 1, and that 1 ends up going all the way over here to our chloride ion, then making its outer shell happy. And so then what we see is that we no longer have this sodium positive cation hanging out, and we no longer have the chloride ion, which is an anion, the negative ion, hanging out. Instead, now they're right next to each other because they're attracted to each other, because this one is more positive and this one's more negative, and so they stick together. And so then what we see is that this is our table salt, and it's actually in a crystalline form. And then this is because we have our chloride ion, and then we have our sodium, and then we have chloride, and then we have sodium, and then we have chloride, and then sodium. So we have all of these stacked up next to each other because they're positively charged and negatively charged. Now, what we've just described here is our first type of chemical bonding. This is called ionic bonding. And as we just went through, ionic bonds, or ionic bonding, is an attraction between a positively charged cation and a negatively charged anion. So our cation, which is our positively charged, and our anion, which is negatively charged. So those want to hang out next to each other because they're very, very positive or they're very, very negative, and then they're going to hang out next to each other and form a bond. This is an ionic bond. So we oftentimes see this in elements that are on the far left and the far right of our periodic table. So let's go to our periodic table for just a moment. So here we see oftentimes a lot of the elements over in this area and the elements over in this area, not these guys, right, because these are already stable here, but they're going to form ionic bonds. And actually, let's move back over here. So we have our ionic bonds, which is where we are gaining or losing electrons. Where is our ionic bond? There we go. So in an ionic bond, the keywords here are gaining and losing electrons. So one is going to lose electrons, and then one is going to gain electrons. And so then that's how we form our ionic bond. So that's the first bond that you should be familiar with. The next bond that you should be familiar with is something called a covalent bond. So covalent bonds, or bonding. All right, so when we're talking about covalent bonds, this is different than our ionic bonds in that we're not gaining or losing electrons. In this case, we are sharing electrons. So this is when our two atoms are going to share. So atoms can share 1, 2, or 3 electrons. And that gives us our single, double, or triple bonds. Oftentimes you'll see this. So if we did water, for example, we have an oxygen, and then when we draw these lines to hydrogen, this line right here indicates a single bond. And we'll take a look at why that is in just a moment. So that would be a single bond. Then we can also see things like double bonds. So let's say there's a carbon double bonded to a nitrogen. This would be a double bond. And then sometimes we also see triple bonds. Let's just do a carbon triple bonded to another carbon. So in this case, we've got our triple bond. So the lines indicate different bonds when we're talking about covalent bonding. So again, in covalent bonding, our atoms are sharing electrons. And then this is going to allow both of those atoms, or multiple atoms, to fill that outer shell. So let's take a look at this one here. Let's take a look at water. So oxygen. Oxygen has, let's see, we'll just try here. Oxygen has 8 protons. So we're looking at 8 electrons. and then hydrogen has one proton, so 1 electron. So if we're looking at our hydrogen, which is pretty basic here, we have a single electron shell and it's got 1 single electron. So we're missing this electron here. If you look at oxygen, we have our first shell, which has 2. Our second shell, so we're at 2, 3, 4, 5, 6, 7, and I'll put the other one here, 8. Okay, so that's 8 total electrons, which means that we're missing 1 here and 1 here. So rather than it being an ionic bond, a case where we're looking at gaining electrons here or losing the electrons we have in the outer shell, in this case what we're talking about is sharing. So if we're going to share, that means that oxygen is looking to bond with 2 bonds, right? So we need to get 2 electrons here. So that can either be a double bond with something else, or it can be 2 single bonds. So it is looking to do that, and oftentimes we see it doing that with hydrogen in order to make water. So hydrogen over here, remember it has 1 single electron, it's missing 1 electron, it also wants to fill its outer shell, which is its only shell, and so we see a sharing of electrons. And if I draw that down here, we have our nucleus, our inner shell. I'll just put 2 here and then 2 here for ease. And then we have this. So these are 8 electrons that we find in oxygen. Then if we put a hydrogen here, then they can share this electron here. I'm going to make it bigger just to really illustrate it. So in this case, this was the electron that came from the hydrogen, right? So its 1 electron is going to be shared with oxygen, and then oxygen's electron here that it brought to the party is going to be shared with hydrogen. So these electrons then are going to be flying around both oxygen and hydrogen. And then we can do the same over here. We can add our hydrogen. We have this electron that came here from oxygen, and then we have the electron, I'll make it bigger, that came from hydrogen. So again, over here, then we have this oxygen sharing electrons with this hydrogen now. So it's sharing hydrogen or electrons with the bottom hydrogen and the side hydrogen. And then what this does is it kind of gives both of them a full outer shell. The electrons spend enough time around the oxygen that it is happy and no longer looking to interact. And they spend enough time around the hydrogens so that they are no longer interacting. And they're forming this bond. Remember, this is our covalent bond. So we have our oxygens and our 2 hydrogens. And we see this happen with other things as well. So if we wanted to take a look at one other example really quick before we go on to the next thing here. If we looked at, let's say, carbon. So remember, 6 protons, which is 6 electrons, and then let's say with hydrogen, which we already know up here. So if we look at carbon, again we have its inner orbital, gives us 2, and then we have its outer, which has 4, right, because we have 6 total, 1, 2, 3, 4, 5, 6. So we're missing these 4, and then what we can see is that carbon is going to share. So we'll share with the hydrogen here, which means that we have these 2 electrons here forming a single bond. We share with a hydrogen over here, so these are single bonds. Single bonds means they're sharing 2 electrons. Okay, so if it's sharing more than 2, then it would be a double bond, right? So if it's sharing 4 electrons, it would be a double bond. If it's sharing 6 electrons, then it would be a triple bond. So here we are, here's a methane molecule, which is a carbon with 4 hydrogens. So carbon, hydrogens times 4. So CH4 is our methane molecule. And of course over here I didn't write the chemical equation, but H2O, because they're hydrogens times 2 and an oxygen. Carbon, 1 of them, and then hydrogens, 4 of them. So we see the same type of covalent bonding here. So carbon and hydrogens, let's say 4 of them for methane, and the oxygen with 2 hydrogens are both going to be types of covalent bonding. And the key word there is different types of covalent bonding. So there are actually 2 different types of covalent bonds that you need to know. So the first type of covalent bonding that we're going to talk about, or actually both of them really, are polar. So we have polar bonds and nonpolar bonds, and these are both forms of covalent bonds. So we have polar covalent bonds and nonpolar covalent bonds. So our polar covalent bonds means that the atoms do not share electrons evenly. So then nonpolar, meaning not polar, is where our atoms share. They share nice. They share electrons evenly. So polar atoms do not share the electrons evenly, and nonpolar, where they do share evenly. So let's take a look at that, because this is a very, very important thing to understand as we're moving through the different systems. So let's look back up here at our example of our methane and our water. If we look here, actually, let's go to our periodic table. Hold on a moment. We'll zoom out, head back over to our periodic table, and talk about electronegativity for a moment. So electronegativity, I'll write that down here. Electronegativity. So electronegativity is basically how strongly an atom pulls on electrons. If we look at our periodic table of elements, generally the trend is that as we go left to right across our periodic table of elements, we go from less electronegative to more electronegative. As we go from bottom up toward the top, we go from less electronegative to more electronegative. So with the exception here of our noble gases, which don't count because they don't want to interact with anybody, this means that up in this region we have our more electronegative atoms, versus over in this region we have our least electronegative atoms. I don't care, it's not important whether or not you know which one is more electronegative than another on the periodic table of elements. That's something that you may need to know for chemistry. But what's important here is that you understand the concept of electronegativity as it relates to our covalent bonds. So if we look at these molecules here, so if we look at our methane molecule, our carbon and our hydrogens are pretty close in the amount of electronegativity that they have. So the amount of electronegative the carbon is about equal to the amount of electronegative the hydrogens are. So what ends up happening is we have an equal sharing, right? So our methane molecule here would be a non-polar molecule. That would be a covalent bond that is nonpolar. What that means then is that we have our carbon in the middle, right? And we have our electrons that are flying around this carbon. And then we have our hydrogens that it has become covalently bonded to. What that means is that the electrons spend about as much time around the carbon as they do around these hydrogens. So they're sharing them pretty evenly. So everybody is really happy. We go around our hydrogens, we go around our carbon. So everybody is getting about the same amount of electron time. In our polar, remember our polar covalent bond, this is where they do not share them evenly. So if we look at our oxygen is very electronegative. What that means then is it's pulling really, really hard on the electrons. So it's pulling and pulling and pulling, and it has bonded covalently to these hydrogens, but it hardly ever lets those hydrogens spend time with the electrons. So we see a buildup of negative energy, right, negative charge around this oxygen compared to our hydrogens. You see that our oxygen has built up a lot of black marking here because it is very, very electronegative. It's pulling those electrons toward it. It gives the electrons to the hydrogen sometimes just so that it feels happy, that it has its outer shell filled, but mostly it spends its time around the oxygen. What that means then is that this molecule, being polar, ends up having a partial negative, this is for partial here, partial negative charge on the oxygen, and the hydrogen has a partial positive charge, right? Because if we're pulling negativity away from those hydrogens, they're going to be more positive. And if we're pulling the oxygen here, if we're pulling negativity toward the oxygen, it's going to be more negative. So this is our polar covalent bond, where we have one atom or more atoms that are pulling on the electrons and not sharing them very evenly. And this actually is going to lead us to our third bond. Our third chemical bond that we're going to talk about is the hydrogen bond. Unlike our ionic bond and our covalent bonds, both polar and nonpolar, our hydrogen bond is a weak and temporary interaction. So our hydrogen bond is weak, it's temporary, so it breaks and it forms over and over again. And this is an interaction between polar molecules. We do see this often in water, and that's the example that I'm going to use, but it can be any polar molecules, because remember, if we're talking about polar molecules, we have this partial positive on one end and then a partial negative on the other. And since we do have this partial positive and this partial negative, remember, a positive is going to be attracted to a negative. We have attractions between polar molecules. When we looked at our methane molecule, remember, it is nonpolar. It shares electrons equally. It doesn't have any sort of negative or positive charge. Since there is no negative or positive charge, this molecule doesn't interact with other molecules. So it's happy to be there by itself, and it's not going to be attracted to any other molecules or pulled away from any other molecules, repelled from any other molecules. Our water over here, on the other hand, our H2O, our water, is polar. And so we have this partial positive and the partial negative, which is going to create hydrogen bonds, which are these weak temporary interactions between polar molecules, because what we see then is our partial negative of the oxygen and our partial positive on the hydrogens are then going to be attracted to the opposite, right? So we have our hydrogen, which is partially positive, is going to be attracted to our partially negative oxygen on another molecule, on a water molecule, for example. So this right here is our hydrogen bond. So we have our partial positive of the hydrogen, our partial negative of the oxygen. Those are attracted to each other, forming a temporary bond. And we see this on all of the water molecules. So over here we have our other partially positive hydrogen. So what we see then is we have our partially negative oxygen from another molecule create a hydrogen bond with that hydrogen. And we see this molecule after molecule after molecule. We see the same thing here. So let's say this, our original oxygen on the original water molecule, then is going to be attracted to our partial positive on another water molecule. And it just keeps building and building and building. That gives us water. So these are the dotted lines here are our hydrogen bonds. And again, it's the positive end of one water molecule, the hydrogen, is going to be attracted to the negative end of the other, which is the oxygen. And it's going to hold these together, and it holds them together weakly, like we see in water. So water is polar. The oxygen pulls the electrons from the hydrogens, so the oxygen end is more negative. The hydrogen end is more positive. And so then we have these partial positives, partial negatives that are going to then cause attractions. And so this is why we see water is cohesive. It has cohesion and adhesion, which we'll talk about when we talk about water. But these properties come from the hydrogen bonds. And so we actually see these in other things as well, and we'll talk about those as we move through the semester. But it's important to understand that we have these 3 different types of bonds. Remember our ionic bonds, where we either gain or lose electrons. We have our covalent bonds, which includes our polar covalent and our nonpolar covalent, and then we have our hydrogen bonds. So I'm going to just write that out really quick. Remember our ionic bonds, which are between ions. And this is a gaining or losing of electrons. And then they sit close to each other because they're because they're very positive and very negative, and then they stay next to each other. Then we have our covalent bonds. Our covalent bonds are a sharing of electrons. And in the sharing, we can have our polar covalent bonds, where they share unequally, or nonpolar, where they share them equally. Then we have our third type, which is our hydrogen bond. And remember, our hydrogen bond is a weak bond between our partial positive on one molecule, or one end of a molecule, and our partial negative on another part of a molecule. So those are the 3 types of bonds that you need to be aware of, including the polar and nonpolar aspect of the covalent bonds. And this is going to be important as we talk about water, specifically because it's very special, being that it's polar. But then also as we talk about our different biological molecules that we see, for example, our carbohydrates, our proteins, our nucleic acids, our fats, lipids, all of those things are going to be based on these ideas that you should be familiar with.